All right, let's pull back the curtain on a secret that's hiding in every single wire you use. We're going to get to the bottom of the absolute fundamentals of electricity. We're talking current, charge, and voltage. I mean, think about it. You do it every single day. You plug your phone in, that little screen lights up, and somehow power just flows down that tiny cable. But what is actually happening inside that wire? What's moving? What's giving it the push? Well, by the time we're done here, you're going to know exactly what's going on. So to really crack this everyday mystery, we've got to start with the absolute basics, the things that make all of our favorite gadgets tick. That's right. It sounds complicated, but believe it or not, pretty much all of electricity really just comes down to how three fundamental concepts work together. Let's think of them as the main characters in our little story here. Okay, so let's meet the cast, shall we? We've got charge, current, and voltage. If you can get your head around these three, you've basically unlocked the key to understanding everything else. First up is charge, which we usually just call Q. Now, this is the actual stuff of electricity. It's this basic property that tiny little particles, like electrons, have. A good way to think about it is like charge is the individual drops of water inside a hose, and we measure it in a unit called coulombs. Okay, so if charge is the water, then what's current? Well, current, or I, is how fast that water is flowing. It's the rate of flow of the charge. We're talking about how many coulombs of charge are zooming past a certain point every single second. And that flow, that's what we measure in amperes, or as you probably know them, amps. And that brings us to our third and final player, potential difference. You almost certainly know it better as voltage, or V. So if you've got all this charge, what actually gets it moving in the first place? It needs a push, right? Well, voltage is that push. It's the energy that's given to each little bit of charge that forces it to move. And we measure that push in, you guessed it, volts. And here's where it all kind of clicks into place. When you pick up a 9-volt battery, what that label really means is that for every single coulomb of charge that passes through it, that battery gives it 9 joules of energy. That's the push. Okay, now lean in for this one, because this is a super important point that chips up so many students. In the real world, what's actually moving are these tiny negatively charged electrons, and they flow from the negative side of a battery to the positive side. But for historical reasons, way back from before we even knew what an electron was, we draw our diagrams differently. We use something called conventional current, which we always draw flowing from positive to negative. Just remember, electrons are what's really moving, but in our diagrams, we draw current going the opposite way. So these three, charge, current, and voltage, they aren't just concepts floating around. They're all connected by some really simple, really important formulas. And these are the formulas you're absolutely going to need for your exams. The first big formula you need to know connects current and charge. It's simple. Current, I, is just the amount of charge, Q, that flows, divided by the time, T, it took to flow. So if you have 1 coulomb of charge passing a point in 1 second, congratulations, you've got a current of 1 amp. And the next one links voltage to energy. Voltage V is equal to the energy transferred, that's E, divided by the amount of charge, Q, you moved. See how that perfectly matches our definition? It's the amount of energy given to each unit of charge. Okay, but how do you actually measure this stuff in a real lab, in a real circuit? Well, we use 2 different kinds of meters. To measure the current, you use an ammeter, and you have to put it in series. That means you break the circuit and put it right in the path of the flow. But to measure voltage, you use a voltmeter, and that goes in parallel. You connect it across the component you want to measure. Okay, theory is great, but let's put this into action. Let's run through a couple of worked examples, the kind of thing you're definitely going to see on a test. All right, first up, the problem says a current of 3 amps flows for 12 seconds. How much charge went by? Well, we start with our formula, I equals Q over T. We just need to rearrange that to find Q, so Q equals I times T. Then we plug in our numbers, 3 amps times 12 seconds, and that gives us our answer, 36 coulombs. See? Not so bad. Ready for another one? Let's do it. This time, we've got a 6-volt battery, and it transfers 120 joules of energy. The question is, how much charge did it move? So we grab our other formula, V equals E over Q. We rearrange it for charge, which gives us Q equals E divided by V. Pop in the numbers, 120 joules divided by 6 volts, and boom, we get our answer, 20 coulombs. It's a great example of how you can use different pieces of information to get to the same answer. Okay, now, for what might just be the most important part of this whole explainer. We know the ideas, we know the math, but now let's talk about the common traps people fall into, so you can just step right over them. So here we go, 5 traps you absolutely want to avoid. Number 1, getting confused about which way things flow. Remember, conventional current is positive to negative, but the electrons themselves go negative to positive. 2, don't mix up current and voltage. Current is the flow, voltage is the push. 3, get your meters in the right place. Ammeters go in series, voltmeters go in parallel. 4, please, please, please always write your units. C, A, V. Get those easy marks. And finally, number 5, just make sure you pick the right equation for the job based on the information they give you in the question. So let's bring it all home. We've learned that voltage is the push and current is the flow of charge that happens because of that push. But in any real wire, there's always going to be something fighting back, something trying to slow that flow down. So the big question is, what's trying to stop it? Well, that is a whole other story, a story all about resistance.